Today we'll start the another method, that is displacement method of analysis. So already you know that is the flexibility method of analysis, how you have to solve the problem, and here also this is another matrix method. So you can also solve any kinematically determinate or indeterminate structure by these methods. So this method is also known as stiffness method or equilibrium method. In this method, the degree of kinematic indeterminacy, the degree of freedom of a structure is to be determined, and the coordinate is assigned to each independent displacement components. So you know what is the degree of kinematic indeterminacy or degree of freedom? You know what is the degree of kinematic indeterminacy? Degree of kinematic indeterminacy is also known as degree of freedom. When the unknown displacement components cannot be found out using the compatibility equation, then that is called the kinematic indeterminacy. To find out the unknown displacement components, so you need that extra static equilibrium equations. Then you can find out the unknown displacement components. If the unknown displacement components is greater than the compatibility equation, then the structure is kinematically indeterminate. The number of extra static equilibrium equation is required to find out the number of unknown displacement components. So that is called the degree of kinematic indeterminacy, or this is also called the degree of freedom. Already we have discussed in last semester that is your statically determinate or indeterminate structure, or kinematically determinate and indeterminate structure. So in the case of rigid jointed plane frame, what is the degree of kinematic indeterminacy? dk is equal to 3j minus r plus m. In the case of inextensibility of the member, but when extensibility is considered, so that case dk is equal to 3j minus r. So j is the number of joints and r is the number of reaction components. But in the case of space frame, extensibility of the member, so the formula dk is equal to 6j minus r in the case of space frame. When you are considering the inextensibility of the member, so that case the degree of kinematic indeterminacy is equal to dk is equal to 6j minus r plus m. And also in the case of pin jointed plane frame, so the dk is equal to 2j minus r. And in the case of pin jointed space frame, so that case the dk is equal to 3j minus r. 3j minus r. In this method, so first you have to find out the degree of kinematic indeterminacy, and the coordinate is assigned to each independent displacement components. In general, the displacement components are the supports, and joints are treated as independent displacement components. Let 1, 2, n are the coordinates assigned to these independent displacement component delta 1, delta 2, delta n. So along this coordinate direction, you have to assign the independent displacement component, that is your delta 1, delta 2, and up to delta n. Lock all the supports and joints to obtain the restraint structure in which no displacement is possible at the coordinates. So first what you have to do, lock all the supports and joints, or restrain all the joints in which no displacement takes place at any joint. So let P1 dash, P2 dash, Pn dash are the forces required at the coordinates 1 to n in the restraint structure. So you have to find out along each coordinate direction, show the force P1 dash along the 1 coordinate direction, and along 2 coordinate direction P2 dash. Similarly, along n coordinate direction, the force is Pn dash. That you have to find out, in which the displacement delta 1, delta 2, and delta n is equal to 0. Because you have restrained all the supports and joints, so that there is no displacement takes place, and you have to find out what is the forces at each coordinate direction. Let the support and joints be unlocked and permitting displacement. Then what you have to do? So you have to unlock first one coordinate, and other coordinates are locked. You have to allow for displacement in for first coordinate, then you have to go for the second coordinate, and all others are restrained. Then you have to go for the release the third coordinate, then all others are restrained. Similarly, you have to go for the nth coordinates, you have to release nth coordinates, and all others are restrained. So let the supports and joints be unlocked and permitting displacement delta 1, delta 2, delta n at the coordinates. These displacement required forces P1 delta, P2 delta, Pn delta at coordinate 1, 2, and n respectively. This is the force at the coordinates. If P1, P2, Pn are the external forces at coordinates 1 to n, then the condition of equilibrium of the structure may be expressed by the equations. This is the external forces P1, P2, Pn at coordinate 1 to n. These are the condition of equilibrium of the equations. So P1 is equal to P1 dash plus P1 delta, P2 is equal to P2 dash plus P2 delta, Pn is equal to Pn dash plus Pn delta. Then you write this in matrix form. This is expression 1. Equation 1 may be expressed in the matrix form P. So this is the column matrix P1, P2, P3, Pn. Then P1 dash, this is your P dash. This is also column matrix, and P delta, this is also column matrix. P is equal to P dash plus P delta. But you know, so P1 delta is equal to K11 delta. So this you can find out by releasing one joint at first coordinate. So you have to find out what is the force required due to the displacement at the coordinate 1. So here you see K11 indicate the force at coordinate 1 due to displacement at coordinate 1. Similarly, K12 indicate force at coordinate 1 due to displacement at coordinate 2. And here this is force at coordinate 2 due to displacement at coordinate 1. This column is your force at coordinate 1, 2, 3, n due to displacement at coordinate 1. Similarly, this column is your force at coordinate 1, 2 due to displacement at coordinate 2. So these are the expression P1 delta, P2 delta, and Pn delta. Then after putting the above value in equation 2, so you have to put this value here in P delta. So after putting here, so P, this is your P, P1, P2, P3, Pn, and P dash, this is your P1 dash, P2 dash, Pn dash, and P delta, P1 delta, P2 delta, Pn delta, that you have to put here. So after putting, this is the expression. P1 is equal to P1 delta plus K11 delta 1. So this is the expression. This is your equation 3. Then you can write this equation in the matrix form. You can maybe express in the matrix form. So P, this is the column matrix P, and this is also column matrix P dash plus, and this is your called the stiffness matrix. K11 delta, K12 delta, K1 n delta n, K21 delta 1, K22 delta 2, K21 delta n. Similarly, Kn1 delta 1, Kn2 delta 2, and Kn delta. This is your called the stiffness matrix. So that you can denote by K, stiffness matrix into delta, K into delta. This is your K into delta. So solving equation 4 for unknown independent displacement components. So you can find out what is the displacement here. So displacement is equal to K inverse. You take this side, P minus P dash and K inverse. If the external forces act only at the coordinates, the terms P1 dash, P2 dash, Pn dash is your vanish. If the external forces are acting at the coordinates, assigned the coordinate direction, so this case, the P1 dash, P2 dash, and Pn dash is equal to 0. So this is your 0. So the equation becomes delta is equal to K inverse P. K inverse P. Equation is. On the other hand, if there are no external forces at the coordinates, if there is no external forces at the coordinates, so that case, so this is your 0. P is your 0. P1, P2, Pn, this is your 0. So the equation becomes a minus of K inverse P dash, minus of K inverse P dash. So this is your equation 7. After computation of this displacement, the bending moment in the member of the structure may be calculated using the slope deflection equation. You know already the slope deflection equation. So using slope deflection equation, after getting the displacement, you can find out the bending moments in the member of the structure. So this method is applicable to static, determinate as well as indeterminate structure. The method is known as displacement method because in this approach, the displacement are treated as unknowns. Why this is called the displacement method? Because the displacement are treated as the unknowns. Because you have to find out the displacement. You have to find out the displacement. So after getting the displacement, then you can find out what is the bending moment using the slope deflection equations. So after knowing the deflection, you can find out what is the bending moment using slope deflection equation. That's why this is called the displacement method. And why this is called the stiffness method, stiffness matrix method. The stiffness matrix is developed for the structure, so that the method is also known as stiffness method. Because here you have to develop the stiffness matrix. This one. This is the stiffness matrix that you have to. So that's why this is called the stiffness method. And also this method is also called the equilibrium method. The condition of equilibrium of the structure is utilized for the determination of displacement. The method is also named as equilibrium method. So these are the different steps you have to remember for the analysis of any continuous beam or frame using this method. These are the steps. The first is you have to find out the degree of kinematic indeterminacy or degree of freedom. You have to find out this one first. Then identify the independent displacement component. Then you have to identify. So if the degree of kinematic indeterminacy is 2, then you have to choose 2 independent displacement components and you have to assign that 2 coordinates. If the degree of kinematic indeterminacy is 3, then you have to choose the 3 independent displacement components and you have to assign 3 coordinate direction. So second is you identify the independent displacement components, then assign the coordinates 1, 2, and to the independent displacement components. Then prevent all the independent displacement components to obtain the restraint structure. Then what you have to do? So you have to prevent all the independent displacement components. You have to restrain all the supports and joints. If the support and joint is a restraint, then there is no displacement takes place. You see, in the case of fixed beam, so due to the fixed end at both ends, there is no displacement takes place. There is no displacement takes place. So the displacement at the fixed beam, fixed end is 0. But you see, in the case of cantilever beam, so in the fixed end side, there is no displacement, but in the opposite side, there is no support. So there is a displacement takes place along 3 directions: vertical direction, horizontal direction, and also rotational displacement. That's why what you have to do? So prevent all the independent displacement components to obtain the restraint structure. You have to make all the joints and supports are restrained or fixed so that there is no displacement takes place. Then you have to find out, determine P dash, the forces required are the coordinates in the restraint structure due to the loads other than those acting at the coordinates. Then what you have to do? What is the force you have given in the beam? So due to that force, due to that external load or the force, you have to find out what is the forces at the coordinate direction. You have to find out. In the restraint structure means you have to make all the supported joints are fixed. Then you have to find out what is the fixed end moments. You have to find out at the end of the member what is the fixed end moment. Then at the joint, you have to take the sum of the 2 fixed end moment of both sides of the joints. Then you can find out what is the forces are the coordinates. Then determine P delta, the forces required are the coordinates in the on restraint structure to cause the independent displacement components delta. Then you have to find out by on restraining first coordinate, then you have to find out what is the forces due to the unit displacement at coordinate 1. What is the force at coordinate 1 and what is the force at coordinate 2. Then you have to another coordinate, you have to delete that coordinate. Again, you have to find out what is the force due to the displacement, unit displacement at the coordinate 2. So that way you can find out the stiffness matrix, compute the net forces. So this is the net forces. P is equal to P dash P delta. So this from this P delta, use the condition of equilibrium of forces to compute the displacement. Then you know P delta is equal to K into delta. So after putting this, Then after simplifying, so delta is equal to k inverse p minus p delta. This is the displacement. So you have to find out the displacement. So after knowing this displacement, you have to compute the internal member forces, that is the bending moment, using the slope deflection method. So these are the steps. So you have to remember these steps. Now you are clear. First you have to find out degree of kinematic indeterminacy. Then identify the independent displacement components. Then you have to assign the coordinate direction. Then prevent all the independent displacement component to obtain the restraint structure. Then you have to find out the P dash due to the given forces other than the force acting at the coordinates. Then you have to find out P delta, that is the stiffness matrix you have to find out. Then you have to find out P total force is equal to due to the given force external load, and this is due to the unit displacement at coordinate 1 and coordinate 2. This is P delta K delta, K into delta. So this is the stiffness matrix you have to find out using this one. Then use the condition of equilibrium of forces to compute the displacement. So this is the expression. Using this expression, you can find out what is the displacement. So, and finally, you can find out what is the bending moment, using the slope deflection method. Now we'll discuss one question, then you will be clear. So this is your question. Analyze the continuous beam shown in figure by displacement method. Take EI constant throughout. This is your continuous beam. This is your support ABC, and AB length 4 meter, and BC length is your 3 meter. And one concentrated load is your present 100 kilonewton at a distance 1.5 meter from the support C. And here the UDL is your present throughout the span. AB length is your 4 meter. Load is your 60 kilonewton by meter. So what you have to do? First you have to find out the degree of kinematic indeterminacy. So this is your rigid jointed on-braced plane frame. So this is the equation. The degree of kinematic indeterminacy is equal to 3j minus r plus m. So j is the number of joints, and r is the number of external reaction components, and m is the number of members. Here 2 members. So how many joints are here? 3 joints. Then how many reaction component? Here 3. Fixed means there is your 3 reaction component, and this is your 1 reaction component. Here 1 reaction, vertical reaction only. Then how many members? 2 members. M is your 2. So dk is your equal to 3j minus r plus n. 3j, 3 into 3 minus r is your 5, and m is your 2. So the degree of kinematic indeterminacy is your equal to 2. So you have to choose 2 unknown displacement components, because dk is your equal to 2. So the unknown displacement in this problem are the rotation at B and rotation at C. So here you see, here there is no displacement takes place, only the displacement takes place at 2. That's why the degree of kinematic indeterminacy you got here 2. Means here the rotational displacement takes place, and here also rotational displacement takes place. There is no vertical displacement due to the support, because this is the support. So there is no vertical displacement takes place here, and there is also no vertical displacement takes place. And you are considering the inextensibility of the member. This formula is for the inextensibility of the member. So there is also no horizontal displacement. There is also no horizontal displacement. So that is also 0. Only the displacement takes place here, rotational displacement, and here also the displacement takes place, rotational displacement. So you have to consider this is one displacement and this is another displacement. You have to assign the coordinate direction. Here 1 and here 2. At B you have to assign coordinate 1, and at C you have to assign coordinate 2. So at B and C, so there is a 2 unknown displacement components. This one, and the coordinates selected at B and C is your 1 and 2, because here there is a rotational displacement takes place, unknown displacement, and here also unknown displacement. The rotational displacement is your at C. So you have to assign the coordinate at B and C, 1 and 2. Coordinates selected. Then what is your next step after choosing the coordinate? What is your next step? After choosing coordinate, So your next step is so here we have identified two independent displacement components. Assign the coordinates 1, 2. So here assign the two coordinate into independent displacement components. Then the next is prevent all the independent displacement components to obtain the restraint structure. Then what you have to do? So here you have to prevent displacement at B and displacement C. So what you have to do? You have to restrain B and restrain C. Means you have to make this is your fixed and also this is your fixed. So there is no displacement takes place at any joint or support. Prevent all the independent displacement components to obtain restraint structures as shown in figure 1C, fully restrained structure. Then the next step is determine P dash. The forces required are the coordinates in the restraint structure due to the loads. So here you see, so this is the load present on span AB and this is the load present on span BC. So due to this force, what is the friction moment AB and what is the friction moment BA? So friction moments MFAB is equal to minus WL square by 12 minus 60 into 4 square by 12 minus 80 kilonewton meter, and MFBA is equal to plus 60 into 4 square by 12. So this is a plus 80 kilonewton meter. Similarly, so for span BC, this is fixed. So you have to find out MFBC and MFCB. So because this is the concentrated load present at the midpoint of BC, so what is the friction moment at B and what is the friction moment at C? So MFBC is equal to minus WL by 8 and this is plus WL by 8. So this is minus 37.5 kilonewton meter. This is plus 37.5 kilonewton meter. Then the forces developed in the coordinate direction due to given load are, so this is force, this is also force, this is force, moment or force, all are forces you have to consider. So you have to find out at coordinate 1, what is the force. So from this span, what is the moment here? So you have to take the sum of the moment at B and that is the force you are acting at coordinate 1. Similarly at coordinate 2, so what is the moment you are here? You got what is the moment here, MFCB. So this is the force acting at coordinate 2. So P1L is equal to MFBA plus MFBC. So MFBA this side, MFBC this side. So this is the force P1 acting here. P1 due to load P1L and P2L. This is your P1L. P2L is equal to MFCB. MFCB. What is the friction moment here? So this is your equal to P12. So you can denote this is your P1L, P12 or P1 dash or P2 dash or P1L, P12 because this is your due to the external loading. So P1L and P2L. The above forces are positive. This forces are positive and this is also positive if they act in the positive direction of the coordinate. So this forces are acting positive direction of the coordinate. Then you have to find out forces in the on-restraint structure. So first you have to find out the force in the restraint structure due to the given loading. Then you have to find out the forces in the on-restraint structure by applying the displacement, the unit displacement at coordinate 1 and what is the force at coordinate 1 and what is the force at coordinate 2. Then by applying unit displacement at coordinate 2, you have to find out what is the force at the coordinate 1 and what is the force at the coordinate 2. First you apply unit displacement in coordinate direction 1 because this is the rotational displacement. Rotational displacement, you have to take bending moment means you have to take rotational displacement. So theta is you have to apply 1, you have to give theta is equal to 1. And you have to find out K11, the force at coordinate 1 due to unit displacement at coordinate 1. And this is your force at coordinate 2 due to unit displacement at coordinate 1. Then one radiation rotation is given to the support B in coordinate direction 1. Then forces developed in the coordinate direction 1 and 2. You have to find out the forces developed due to this theta is equal to 1 here and here. At 1 and 2 are found by using slope deflection equation. You have to find out this force you are using the slope deflection equation. You know in the slope deflection equation, here you see, then you will find out here this side, when you are considering this side, K11, you have to find out K11. So you have to find out from this span and you have to find out from this span. When you are considering this span, so this is your theta A and here theta b, and here theta c. But theta b is your equal to 1. Theta b is your equal to theta is your equal to 1, and theta is your 0, and theta c is your equal to 0. So what is the formula? So here you see from this side 2e I theta I by 4, and from this side 4ei theta b by 4. From this one, and from this one, so here 4ei theta b by 3. The span length is your 3, BC span length is your 3, and AB span length is your 4. That's why you know that is 2ei theta by L and 4ei theta by L. So 4ei theta is your from that from this side is your 4 and this side is 2. Here also from this side is your 4 and from this side is your 2. So 4ei theta b by 3 and plus 2ei theta c by 3. Then you have to here theta is your equal to 0 and theta c is your equal to 0 and theta b is your equal to 1. So just to put here that value, theta is 0, theta c 0, and theta b is your equal to 1. So you got here k11 is your equal to 7 ei by 3. You got here k11 7 ei by 3. Similarly, find out k21. So using the slope deflection equation, what is the k21? K21 is your equal to here 4 ei theta c by 3 plus 2 ei theta b by 3. 4 ei theta c by 3 plus 2 ei theta b by 3. But you know theta c is your equal to 0 and theta b is your equal to 1. So after putting this value, so the k21 is your equal to 2 ei by 3. Then what you have to do? Then you have to restrain joint B and you have to release the joint C. You have to release joint C and you have to apply the unit displacement at joint C. That is along the coordinate direction. 2, you have to apply the unit displacement, unit rotational displacement. Theta C is your equal to 1. So this case, theta is your 0, theta b 0 because this is restrained and this is released in second case. And one radiation rotation is given to the support C in the coordinate direction 2. In the coordinate direction 2, and the forces developed in the coordinate direction are found. What is the force developed at B at coordinate 1 and at coordinate 2? Similarly, here also you have to find out what is the force K12 due to the unit displacement at the coordinate 2. Then you have to find out force at 2 due to unit displacement at coordinate 2, K22. So K12 is your equal to 4 ei theta b by 3 plus 2 ei theta c by 3. But you know theta b is your 0 and theta c is your equal to 1. So after putting this, K12 is your equal to 2 ei by 3. Then find out K22. K22 is your equal to 4 ei theta c by 3 plus 2 ei theta b by 3. Here also after putting this, K22 is your equal to this one. So this becomes the stiffness matrix. K11, K21 and the K12, K22. The final forces acting in coordinate direction 1 and 2 are 0. The final forces are coordinate because there is no forces acting at the coordinate 1 and 2. At a joint or support, there is no external forces acting. So the final forces at the coordinate 1 and 2 is your 0. 0, 0. P1 0 and P2 0. And the stiffness equation is your equal to K delta is your equal to P minus PL. PL. So K, you know, this is the stiffness matrix. This is your stiffness matrix. You got here this 4. This one, and this one, this one. This is the become the stiffness matrix. Then delta is the displacement. You have to find out what is the displacement at coordinate 1 and what is the displacement at coordinate 2. Delta 1, delta 2. And this is the force. There is no external forces you are acting at the coordinate direction. So these forces is your 0, 0. Minus, this is the force you got from the external loading, from the restraint structure. You got, this is the force, 42.5 and 37.5. So after simplifying this one, you can find out. So you have to take the inverse matrix of this one, 7 to 2, 4, inverse matrix. You know that is how to solve this one, inverse matrix. So then you can find out what is the displacement, delta 1, delta 2. After simplifying this matrix. So this delta 1 is your equal to theta b and then delta 2 is your equal to theta c. So here you got the, what is the rotational displacement at 1 and 2. Because that's why this method is called the displacement method. Because here you are getting the displacement at the coordinate direction 1 and 2 and delta 1 is equal to the rotational displacement at B, and delta 2 is equal to the rotation displacement at C, and theta is equal to 0. You know that is the end is your fixed. So after knowing this displacement, then you can find out what is the final moment. So you know in slope deflection method how to find out the final moment. MAB is equal to MFAB plus 4EI theta by L plus 2EI theta B by L. So for this AB span, MAB, MFAB plus 4EI theta by 4 plus 2EI theta B by 4. So here you know what is the fixed moment AB. Already you got. Then this is minus 80 plus here you have to put theta is equal to 0, and theta B you got here, theta B minus 11.875 by EI. So after putting this one, so here you got the final moment. This is minus 85.938 kilonewton meter. Similarly, find out MBA. MBA is equal to MFBA plus 4EI theta B by 4 plus 2EI theta A by 4. So here after putting this one, theta B and theta A, everything, MFBA you got 80. Here this is your MBA is equal to 68.125 kilonewton meter. Similarly, find out MBC for span BC, MFBC plus 4EI theta B by L plus 2EI theta B C by L. Here 4EI theta B by, so span length is your 3. So this is wrongly written 4. So this is your 3. This is your 3. Not 4, huh? So here you see, so MFBC is equal to minus 37.5 and 4EI theta B, here written 3, 4EI 3 and minus theta B is equal to minus 11.875 by EI plus 2EI by 3 minus 22, that you have to put theta C and theta B. Then after simplifying this one, so here you got MBC is equal to minus 68.125 kilonewton meter. Always you have to check MBA plus MBC should be 0 at joint B, MBA plus MBC, because here you got plus and this side you got minus. Then find out MCB, MFCB plus of 4EI theta C by 3 plus 2EI theta B by 3. So after putting this theta C theta B, so here you got 0, because you know at the end this one MCB. So you know the moment is your 0, because that is the simply supported end. Here you see, so the end is your simply supported, and it's, so here there is no moment. So after adding, after finally you will get that moment is equal to 0. So this is the, after knowing this moment, then you have to give the direction of the moment. Then you can plot the bending moment diagram, because after knowing, so what is the moment here you got, and what is the moment here you got, what is the moment here you got, and what is the moment 0 here. So then you can plot the fixed BMD. Then you have to draw the free bending moment over it. Then the net bending moment diagram, the positive and negative you have to cancel. Then the net bending moment, the final bending moment you can plot. So this is the process. So you have to remember the process, how to solve any frame or beam by this displacement method.